separation of immiscibles. First, we are using a separating funnel. So we are saying that two or more. We are saying that immiscible liquids are liquids that do not mix upon being added to each other, where the denser settles at the bottom and the less dense one at the top. Now we are saying that this mixture can be separated using a separating funnel. So using a separating funnel to separate the mixtures that are immiscible. Remember, it is because of the density that this one of the liquid will settle at the top, and then the other one will settle at the bottom. Then we'll have the meeting point where these two will meet. Now at that we'll have the two layers where now they are meeting. Two or more liquids that form layers on mixing are immiscible. So miscible mixtures arrange themselves according to their density. That's now what we are now. That is what it makes them to arrange themselves, the density, depending on the density of the liquid. The denser the liquid, the denser liquid sink to the bottom. Then the less dense liquid floats on the denser one. So immiscible mixtures can be separated from each other by using a separating funnel. But I remember now you will not be in a position to obtain the entire entire liquid that we have placed, that we have mixed now, because there is a layer of the tube where they are now meeting that will have to separate from the. When now we are separating, the first liquid that we will obtain will be the one that is denser, now which now is settling at the bottom of the container that we have used to mix them. Now then we'll have the layer that contains both the dense and the less dense, that we'll have to discard. So some volume of the dense and the less dense will be in that we are discarding, which makes us not to obtain the entire of the volume of the liquids that we have used. Now we carry out the experiment to see. Now we have the procedure. We place about 100 centimeter cubic of water into a 250 beaker. We add about 100 of paraffin into the beaker and then stir. Now here we are mixing water and paraffin. We transfer the mixture into a separating funnel and allow to settle for about 1 minute. We open the tap. Now after mixing them, now we want to separate them. We open the tap, run out the layer on the bottom slowly into a clean beaker. Then after that, we close the tap when the upper layer is close to the tap. Run out the intermediate small amount of the mixture near the tap into a beaker. Then discard. Now remember that the mixture we are discarding contains both the water and the paraffin. Then we run out the remaining upper layer into a clean beaker. We place a portion of the upper and the lower into a watch glass separately. After separating them, then ignite. So the essence of igniting is now to determine which one is paraffin and which one is water. Because paraffin, when we ignite paraffin, so water cannot catch fire, but paraffin will catch fire. Remember that both water and paraffin are all colorless. They are all colorless, so you cannot use color to determine which is water and which is paraffin. So to separate an immiscible mixture of paraffin and water, so we place about 100 centimeter cubic of water into a 250 beaker, add about 100 of the paraffin into the beaker. We stir. So stirring will help us now. We are now in a process of mixing. If they are immiscible, actually they will not mix. So you transfer the mixture into a separating funnel. Allow to settle for about 1 minute, then open the tap, run out the lower layer out slowly into a clean beaker, close the tap. Close the tap when the upper layer is very close to the tap. When the upper layer is close to the tap, we run out the intermediate. Now the intermediate, we say that intermediate contain both the water and the paraffin. Both the water and the paraffin. So small amount of the mixture near the tap into a beaker. Then we discard because now it contains both the paraffin and the water. That's why we are discarding it. And then we run out the remaining upper layer into a fresh beaker. Then we place a portion of the upper and the lower into a watch glass separately, different watch glasses, in fact, separately. After separating it, then we ignite. Then now let's see what the observation, what we observe. Water and paraffin are both colorless liquid, and they form two layers on mixing. Colorless and odorless liquid collected first does not catch fire. So the one that does not catch fire is water. So you're saying that water and paraffin are both colorless liquids. So two layers are formed on mixing. Colorless and odorless liquid collected first does not catch fire. So a colorless and odorless liquid that you are collecting at the first does not catch fire. A colorless liquid with a characteristic smell, collected later or the second catches fire. Remember, paraffin has a characteristic smell, and it catches fire and burn with a yellow smoky flame. So reason as to why you cannot use the smell to say that it is paraffin. Remember, some of the water that is either contaminated or contains some impurities, at some point it will have some smell. So we cannot say that because this liquid has some odor, so we can term it to be paraffin. No, we have to prove it by using the ignition of fire, where the second catches fire and burns with a yellow smoky flame. Then now we explain our observation that we have made. We are saying that water and paraffin are immiscible liquids. So water is denser than paraffin. And when put in a separating funnel, paraffin floats on water. And on opening the tap, water runs out fast. And paraffin, then water and paraffin at the junction of the two is discarded because it is not pure. Because now we are saying that it's now the mixture where now the paraffin and water, they are now meeting. The dense and the less dense are now meeting. So we are saying that it is not pure. That's when we are now discarding it. Now we have how the apparatus are set up. We have the separating funnel. Remember, the separating funnel has a tap. So we have separating funnel. So kerosene will be at the top because now it floats on water. It will be at the top. It is at the top. We have water now at the bottom. Now we have what the containers that we use to collect these liquids. First, we will be collecting water. After collection of water, we'll now have another clean beaker to collect now the mixture of water and paraffin. Because now this is impure, we will discard it. Then we collect kerosene in again a clean beaker. Now in a clean beaker. That's separation of immiscible liquid using separating funnel. So in using separating funnel, remember we say that we will not be in a position to collect the entire volume that we have used. Remember in this experiment, we have used now 100 centimeter cubic of paraffin, 100 centimeter cubic of water. But we are not now in a position to collect them all. Why? Because now at the junction where the paraffin and water are meeting, we are collecting the entire of that mixture, then discarding it because now it is not pure. And upon when we want to, we test to now realize which liquid, to realize the liquid that is water and the liquid that is paraffin. Now to another method of separation, we have sublimation or deposition. So some solids on heating do not melt to a liquid, but changes directly to a gas. The process by which solid changes to a gas is called sublimation. Now, the process by which solids changes directly to a gas, we are calling it sublimation. The gas cools back and changes back to the gas cools and changes back to a solid. The process by which a gas changes to a solid is called deposition. Now, deposition and sublimation, they are just opposite process. We are saying sublimation, the solid is changing directly from solid to a gas, directly from solid to a gas. And then we are saying deposition is the process by which the gas cools directly back to a solid. So we are saying deposition and sublimation are the same but opposite process. They are the same but opposite processes. Where now sublimation is where solids change directly to a gas on being heated, and then deposition is where when gases cool back directly to a solid. Same process, same but different processes. So sublimation and deposition, therefore, are the same but opposite processes. They are opposite processes. So we have some common substances that undergo sublimation. One, we have iodine, that is crystalline in form. Its sublimation takes place in presence of oxygen. The particles overcome force of attraction between them, and therefore sublimation takes place. So we are saying that the first common substance that undergoes sublimation is iodine. Yeah, so iodine is crystalline in form. And its sublimation takes place in presence of oxygen. The particles overcome force of attraction between them, and therefore sublimation takes place. Then another substance that undergoes sublimation and deposition is carbon dioxide, or commonly called dry ice. It turns to a gas at negative 78.5 degrees Celsius. And fog is actually a mixture of cold and carbon dioxide gas. So you have humid air created as the dry ice. So you're saying that now carbon dioxide, or normally called dry ice, turns to a gas at negative 78.5 degrees Now, fog is actually a mixture. Fog is a mixture of cold carbon dioxide gas, humid air that is created as as the dry ice melt. That's created as the dry ice melts. So we say the first one is iodine, the second one is carbon dioxide. Then the third one you have camphor. Which turns into a gas due to its weak forces between the camphor molecules as even an environmental temperature is enough for camphor molecule to escape the surrounding environment. We have camphor. We have camphor. We also have camphor as the third a substance that undergoes sublimation and deposition. Then we are saying that it turns into a gas due to its weak forces between the camphor molecule as even an environmental temperature. Now, just the environmental temperature is enough for camphor molecule to escape the surrounding environment. Then we have ammonium chloride. That also undergoes sublimation and deposition. We have iron 3 chloride, which also undergoes sublimation and deposition. Iron 3 chloride. Apart from iron 3 chloride, we have aluminium 3 chloride, which undergoes sublimation, which its sublimation begins at 50 degrees Celsius with a pressure of 1 Pascal. So sublimation increases as the temperature increases from 50 degrees Celsius, and the rate is too fast at the higher temperatures than 130 degrees, and the proposed temperature is 80 degrees. Now, for sublimation of aluminum to take place, we are saying that higher temperatures will increase the pressure to which the sublimation of aluminium 3 chloride undergoes. It increases, but after now, as the temperatures now are increasing, now when it is beyond 130, now it takes too faster. It sublimates too fast. Now the proposed temperature at which the sublimation of the aluminum 3 chloride should be, the proposed temperature is 80 degrees. Now at this rate, it will take place in a desired way. Now the other substance that undergoes is benzoic acid. So enthalpy of sublimation has been determined for benzoic acid as a function of temperature, as a function of the temperature. In the temperature range from 320 to 370 Kelvin by use of sublimation calorimetric system incorporating a Calvert microcalorimeter. Now, we are saying that the enthalpy of sublimation has been determined for benzoic acid as a function of temperature, and in the temperature range from 320 to 370 kelvins, So those are some of the common substances that undergo sublimation and deposition. We have iodine, we have carbon dioxide, we have the camphor, we have ammonium chloride, we have iron 3 chloride, aluminium 3 chloride, and then we have benzoic acid. Those are the common substances that undergo sublimation and deposition. So if a mixture has any of the above as a compound, then on heating it will change to a gas and deposited away from the source of heating. and deposit away from the source of heating. So the mixture that contains one of these common substances that undergo sublimation will help us to separate it easily, because now we'll just provide heat and it will sublime. So if a mixture has any of the above as a component, then on heating it will change to a gas and be deposited away from the source of heating. Now let's look at now an experiment that will help us understand now an experiment. Let's have the procedure. We are placing about 1 spatula full of ammonium chloride crystals into a clean, dry 100 cubic centimeter beaker. Then we add equal amount of sodium chloride crystals into the beaker and swirl to mix. Now we are using ammonium chloride crystals and sodium chloride crystals. Then now we place the beaker on a tripod stand, put about 100 cubic centimeter of water into another beaker containing the solid mixture. Then ignite a burner and let it and heat the solid Now we are placing about 1 spatula full of ammonium chloride crystals into a clean, dry 100 cubic centimeter beaker. We add equal amount of sodium chloride. Now we are using equal amount of sodium chloride and ammonium chloride. Ammonium chloride crystals into the beaker. We swirl now to mix. Then we place the beaker on a tripod stand. Then we put about 100 cubic centimeter of water into another beaker. We place carefully the beaker containing water on top of the beaker containing the solid mixture. Then we light a burner and heat the solid Now, after having undergone through that procedure, when carrying out that experiment, we'll have observation that we make. With ammonium chloride and common salt mixture, which is now sodium chloride, white fumes are produced. Now the white fumes, white fumes are produced, white sublimate is deposited, and a colorless residue is left. So a colorless residue is left. So that's what we'll observe. That's what we'll observe from the experiment that we are carrying out. We can see now the setup of the apparatus. Now the beaker that has water is on top of the beaker that has the mixture of common salt and we are either using iodine crystals, ammonium chloride crystals, just as long as it is one of the common substances that undergo sublimation. So with now the common salt, then we have the tripod stand, then the source of heat, so in this we are having different experiments. The first one is having iodine and common salt. That's how it is. Then the second one is ammonium chloride and the common salt. Now, after having observed that with ammonium chloride and common salt mixture, white fumes are produced, white sublimate is deposited, then colorless residue is left. But now, when we are using now the iodine crystals with the common salt to form a mixture, we have purple fumes. Remember the other one we had white fumes. But now in iodine crystals, we're having purple fumes produced, dark gray sublimate deposited, then colorless residue left. Colorless residue left. Now let's see the explanation of now the different kind of the experiment that we are carrying out. On heating a mixture of ammonium chloride and common salt, a white fumes of ammonium chloride is produced. White fumes of ammonium chloride are produced. Now the white fumes solidify. The white fumes solidify. Now remember, they are now they sublime. Then later they solidify due to the cold water on top. Due to the cold water on top, they solidify as white sublimate on the cooler part. And now the common salt is left as a residue. Now the common salt is what now we are having as the residue inside the beaker. We're having the residue inside the beaker. Inside the beaker. So because of the we have provided heat now, it helps that the ammonium chloride to do what? To sublime. Then the presence of water, or the presence of cold water, it helps it back to do what? To solidify back, to solidify, and we will have it as ammonium chloride, as ammonium chloride. Then on using now the iodine, and on using the iodine crystals, on heating now the mixture of iodine and common salt, a purple fumes of iodine vapor is produced. Now the purple fumes are the iodine vapor. Purple fumes are the iodine vapor that is produced. So purple fumes solidify to form dark gray sublimate. To form dark gray sublimate on the cooler part, and the common salt remain as residue. Common salt remains as residue. Now that makes it easier in case you have mixed any solid with one of the common solids that are can sublime. Makes it easier to do what? To separate them. Makes it easier to separate them. So we are saying that on heating a mixture of ammonium chloride and common salt, white fumes of ammonium chloride are produced. Now the white fumes solidify as white sublimate, on the cooler parts. Now the common salt remain as residue. Common salt remain as residue. The chemical equation of ammonium chloride solid, then provision of heat to ammonium chloride gas. So you can see the chemical equation. So on heating a mixture of iodine and common salt, a purple fume of iodine vapor is produced, and the purple fumes solidify as dark gray sublimate, on the cooler parts. Now the common salt still remains as the residue. Then now we have the iodine solid. On provision of heat, it forms iodine gas. It forms an iodine gas. So in any mixture, as long as it has one of the common solid that can sublime, it makes easier for us to separate them. We just provide, we make, as it is mixed, we will on the upper part we provide cold water that in return will help so that the one that will sublime to solidify. Now let's look at another method of separation, that is chromatography. Now chromatography is a method of separating components of a solution mixture by passing it through a medium where the different components move at different rates. So we are saying that it's a method of separation of components of a solution mixture. Now it's a solution mixture by passing it through a medium where the different components move at different rates. The different components move at different rates. So chromatography, we are saying, is a method of separating the components of a solution mixture by passing it through a medium where the different components move at different rate. Now, the medium through which the solution mixture is passed is called an absorbent material. Now, the medium through which the solution mixture is passed is called absorbent material. The medium now is what we are calling the absorbent material. Paper chromatography is a method of separating colored dyes by using paper as the absorbent material. Now we are using paper. We are saying that paper chromatography is a method of separating colored dyes by using paper as the absorbent material. Now, paper chromatography. What guys ask here is paper chromatography. We are saying it's a method of separating color dyes by using paper as the absorbent material. Now, since dyes are insoluble in water, ethanol and propanol are used as suitable solvent for dissolving the dyes. You'll find that dyes are insoluble in water. They're insoluble in water, and now we are using ethanol and propanol as we are using them as suitable solvents for dissolving the dyes. So we are using ethanol and propanol as now a suitable solvent for dissolving the dye. So practically, a simple paper chromatography involves placing dye on the absorbent material, adding slowly a suitable soluble solvent on the dye using a dropper. The solvent spread out on the absorbent material, carrying the soluble dye away from the origin. Now, doing it practically, a simple paper chromatography. Bring now a practical simple paper chromatography. We are involving placing a dye on the absorbent material that now we are saying in this case is a paper. It's a paper. We are adding slowly a suitable soluble solvent on the dye. The suitable solvent, we said it's either ethanol or propanol. Now we are using a dropper. Now the solvent spread out on the absorbent material, carrying the soluble dye away from the origin. Now, the spot on which the dye is initially placed is called baseline. Now, that the origin that has now the initial spot, we are calling it baseline. So we say that now before placing the suitable soluble solvent, now they are all on the origin. Now this origin, we are calling it to be the baseline. This origin is called baseline. Now, after addition of the soluble solvent, suitable soluble solvent, now the spots will move from the baseline to other places. Now the spot on which the dye is initially placed is called baseline. The farthest point the solvent spread is called the solvent front. Now, the farthest spot that the farthest point that these spots can reach is what we are calling the solvent front. Remember, we are saying that the origin where these spots are is called the baseline, and now the farthest the farthest line, now the farthest point the spots can reach after the addition of the suitable soluble solvent, we are calling it to be the front. We are calling it the solvent front. We are calling it the solvent front as the farthest point, where any given spot can reach. So the spreading of the dye depends on a number of reasons. The spreading of the dye. Remember now, they are all first on one line, which we are calling the baseline, and the farthest they can go is called the solvent front. But now, for these spots to move from the baseline to the solvent front, is determined by a number of reasons. One being the density of the dye. Remember now, this dye can move according to the density. To choose density. Now, the denser the dye, the less is spread from the baseline. The dense it spreads from the baseline by the solvent, by the suitable solvent that we are using. Now, then we have another reason is thickness of the dye. The dye stick on the absorbent material more than other that do not spread faster from the baseline. When the dye sticks more, so it cannot move further. When the dye is hard, it can stick more, it cannot move further. So that can make it not to move more. So we say that the absorbent material carrying the soluble dye away from the origin. So we say that the origin, we are calling it the baseline. Then the spot on the dye is where is initially placed. We are calling it to be the baseline. We are saying it is called the baseline. Now we say that the farthest point the solvent spread, the farthest point where now the spot can spread is called the solvent front. Now the farthest can be spread by the farthest a dye can be spread by the solvent depends. We say that depends on a number of reasons. One, we say the density of the dye. We're saying the denser the dye, the less it's spread from the baseline. Now, the denser it is, the less it spreads. Now, then the thickness of the dye. Some dyes stick on the absorbent material more than others. They stick on material more than others, thus do not spread far from the baseline. They do not spread far from the baseline. Now we have here an experiment that can be carried out now to see. So we have to investigate the color in ink. That's the first experiment that can be done to investigate the color of the ink. So what we do, we have different methods that can be used. Now the first method, we can place a filter paper on an empty beaker, then drop a blue or a black ink, in the center of the filter paper, and wait for about 1 minute for the ink drop to spread further. For the ink drop to spread further. So now, as we had said, that now we are carrying out now an experiment to show this. So we are saying that we have two different methods. The first one is we place a filter paper on an empty beaker, Then drop up either black or blue ink in the center of the filter paper and wait for about 1 minute for the ink drop to spread further. So we add about 20 other drops of ethanol, waiting for about 1 minute before each addition, and allow the filter paper to dry. That's now the first method. Then the second method, we cut 8 centimeters thin strip of a filter paper at about 3 centimeter, about 3 centimeters on the strip. Place a drop of ink and place the filter paper in a 100 centimeter length, in a 10 centimeter length boiling tube containing 5 centimeter cubic of ethanol. Then we ensure that the cut strip of the filter paper just dips into the ethanol towards the ink mark. We cover the boiling tube and wait for about 20 minutes and remove the boiling tube and allow the filter paper to dry. So we have two methods that we can use to carry out this experiment. Have two methods that you can use to carry out this experiment. So remember, in this experiment, investigating the colors in ink. So we are saying that we place, now the method one, we place filter paper on an empty beaker. We put a drop of either blue or black ink in the center of the filter paper. Then we wait for about 1 minute for the ink drop to spread. Once we place the ink, we wait for it to spread out on the filter paper. Then now, using a clean tit pipette or dropper, we add 1 drop of ethanol or propanol. We remember we said that we are using either ethanol or propanol. So we wait about 1 minute for the ink drop to spread further. Remember, first it spread after having added the ink on the filter paper. Now, after having again added now the suitable solvent, we again allow it again to do what? To spread further from the first spread that happened. We add about 20 other drops of ethanol, waiting for about 1 minute before each addition. Then you allow the filter paper to dry. Then the method two that we can also use, we cut an 8 centimeter thin strip of a filter paper. So that filter paper, we cut just a thin strip of filter paper, 8 centimeters. Then at about 3 centimeters on the strip, we place a drop of ink. Now, when you measure, you just place at about 3 centimeters. Place a drop of ink. Place the filter paper in 10 centimeter. We place the filter paper in 10 centimeter length boiling tube containing 5 centimeter cubed of ethanol. We ensure the cut strip of the filter paper just dips in the ethanol towards the ink. We cover the boiling tube and wait for about 20 minutes. For the 20 minutes and remove the boiling tube. 20 minutes, remove the boiling tube and allow the filter paper to dry. Now, this is how the apparatus will be. In method one, this is how the apparatus will be. Now, remember, now this is the filter paper. The filter paper now we are having now this on the top of the filter paper. Now this is the drop. After having added that drop of the ink, we allow it to do what? To spread. Now for method one, the apparatus for method one, have the empty beaker. We have the filter paper. Then on the filter paper at the center, we do what? We add the drop of black or blue ink. Now later on, after the spread of the ink, we are adding ethanol. Then setup of apparatus in method 2. Setup of apparatus in method 2. We have now 8 centimeter. We have 8 centimeter. We have 8 centimeter of what? Of the filter paper, just a thin one. Then now we are adding we are adding the ink at about 3 centimeters on the strip. We place a drop of ink. And we place a drop of ink at 3 centimeter. Then place down the filter paper in a 10 centimeter length boiling tube containing having 8 centimeters of 8 centimeters. Then at just 3 centimeters, we just measure 3 centimeters. Then you have the drop. Now you can see now the drop is just here. Now it's what we are calling the baseline. Then now, because you have dipped it into now ethanol or propanol, either of the liquid, you can see now we have the spots now after after being dipped in the liquid. Now just after the baseline, the spot on the baseline, we will have a spot that will be now nearer to the baseline. It will be a spot that is denser, or that sticks more compared to the other spots. Now the furthest spot will either be on the solvent front or near the solvent front. So we say that the further it can go is the solvent front. That's the farthest point it can go to. Now we can explain that and say that when a drop of ink is placed on an absorbent material, it sticks. On adding an eluting solvent, it dissolves the dye and spreads out with it. Now the denser and sticky pure dye move least. It moves least. Now when a spot is, I say now when the spot is nearer to the baseline, it will be dense and sticky. Now the least dense and sticky pure dye move farthest. The less dense and sticky will move farthest. Now pure dye will produce the same chromatography if the same eluting solvent is used on the same absorbent material. Now comparing the distance moved by pure dye with a mixture, the colored dye in a mixture can be reduced as. Now from this, we are saying that when a drop of ink is placed on an absorbent material, it sticks. Now on adding the eluting solvent, now the solvent now that we are using, it dissolves the dye and spreads out with it. The dense and the stick pure dye move least. Now the least dense and sticky pure dye move farthest. Now a pure dye will produce the same chromatogram or spot if the same eluting solvent is used on the same absorbent material. Now comparing the distance moved by a pure dye with a mixture, the colored dye in a mixture can be reduced as. Now example one we are showing that the chromatograph of pure dye will have now ABC and a dye. Now the pure dyes are ABC, and now the mixture is D. So we can see it from this that the chromatograph of pure dyes ABC and a dye mixture of D is shown here. So we are saying you have the solvent from the baseline, the most soluble pure dye. Now this is the image that we have. So you can see that we have this diagram here. Now the dotted line the dotted line with red color is what we are calling the baseline. Now the continuous line with the red color we are calling the solvent front. Now you can see that the ABCD spots are on the baseline, Now that's the origin, on the origin. Then you can see that A, B, and C are pure. A, B, and C are pure. A and B and a mixture D chromatograph article distance. So you can see that you have A, then you have B, then you have C. So D have two different spots, meaning that it is not pure. It is not pure. It is not pure. So chromatography showing A, B, C, and mixture of D. So A, B, C are pure, then mixture of D. So then another method is solvent extraction. So it's a method of separating oil from nuts or seeds. So most nuts contain oil. First, the nuts are crushed to reduce their size and increase the surface area. Then a suitable volatile is added. The mixture is filtered, and the filtrate is then allowed to crystallize, leaving oil or fat. Then if the filter paper is rubbed or smeared with the oil or the fat, it becomes translucent. Now this is the test for presence of oil and fat. So we are saying that the solvent extraction is a method of separating oil from nuts or seeds. Now we are saying that most nuts contain oil. Now the first nuts are crushed to reduce their size and increase the surface area. A suitable volatile solvent is added to the crushed nuts or the seeds. And the mixture is filtered. Now the filtered solvent is then allowed to crystallize, leaving the oil or the fat. If a mixture, if a filter paper is rubbed or smeared with the oil or the fat, it becomes translucent. Now that's the test. Now how we can test the presence of the oil or the fat. This is the test for the presence of oil or fat. Now let's look at an experiment that can be done to extract oil from macadamia nut seeds. Now the procedure: crush the macadamia nut seed from the hard outer cover, then place the inner soft seed into a mortar. We add a little sand to assist in crushing. So add a little propanol and continue crushing while adding little propanol until there is more liquid mixture than the solid. So we decant or we filter, then put the filtrate into an evaporating dish. Evaporize the solvent using solar energy or the sunlight. Then we smear the portion of the residue left after evaporation on a clean dry filter paper. So now we are having here a procedure. Of extracting oil from macadamia nut seeds. So we have the first one: we crush the macadamia nut seed from the hard outer cover. We place the inner soft seed into a mortar. We crush. On crushing, we are saying that we add a little sand to assist in crushing. So add a little propanol and continue crushing. Then add a little propanol as we continue crushing. Until there is more liquid mixture than the solid. So we are adding the propanol until now the liquid mixture is more than the solid. Then now we filter we filter, then we put the filtrate into an evaporating dish. We evaporate the solvent using solar energy or the sunlight. Then we smear a portion of the residue left after evaporation on a clean dry filter paper, on a clean dry filter paper. So we can see that from what we are seeing, from what we are doing, we can have some observation. The propanol dissolve fat or oil in the macadamia nut. So propanol is more volatile. It's more volatile solvent. So and the lowering the boiling point than the oil, or the fat. So in sunlight or the solar energy, propanol evaporate, leaving oil and fat. That means that it has higher boiling point. So any seed like corn, wheat, rice, or soya beans may be used instead of macadamia seed. When oil and fat is rubbed or smeared on a paper, it becomes translucent. So we are saying that propanol dissolves in fat or oil in the macadamia nuts. Propanol is more volatile, has lower boiling point than oil and fat or fat. In sunlight or the solar energy, the propanol evaporates, leaving the oil or the fat. And now it has a higher boiling point. Higher boiling point. Now it vaporizes fast. So any seed like corn. So you're saying that other than macadamia, you have corn, wheat, rice, soya, have soya beans may be used instead of the macadamia seed. So when we are testing the presence of the oil or the fat, so we smear or we rub on an opaque paper, and the opaque paper becomes translucent. The opaque paper becomes translucent. That's now the test that can show us the presence of the fat or the oil. The fat or the oil. Then we have another method of separation, which is crystallization. Another method of separation, which is crystallization. Crystallization. Crystallization is a process of using solubility of a solute or solid to obtain the solute. It's a process of using solubility of a solute to obtain the solute crystals from a saturated solution by either cooling or heating the solution. So you're saying that it's a process. Now it's a process of using solubility of the solid to obtain the solid itself crystal from a saturated solution by either cooling or heating the solution. Now a crystal is a smaller regular shaped particle of a solute. So every solute has a unique shape of its crystal. Every solute has a unique shape of its crystal. So some solutions from crystals when heated, some solutions form crystals. Some solutions form crystals when heated. This is because less solute dissolve at higher temperature. So, where some other solution form crystal when cool. This is because less solute dissolve at lower temperature. So we say that a crystal in this is the smallest regular shaped particle of a solute, and every solute has a unique shape of its crystal. So some solution form crystals when heated. Some solution form crystals when heated. This is because solute dissolve at higher temperature. Then some other solutions form crystal when cooled. This is because less solid dissolve at lower temperature. Now let's look at an experiment to crystallize copper 2 sulfate solution. Now we have an experiment to crystallize copper 2 sulfate. Solution. Copper 2 sulfate solution. Now you have the procedure. We place about 1 spatula full of the hydrated copper 2 sulfate into 200 cubic centimeter of distilled water. Now we are placing the hydrated copper 2 sulfate into distilled water. Then stir as we continue adding a little more of the hydrated copper 2 sulfate crystals and stirring until no more can dissolve. Then we filter and cover the filtrate with filter paper. We cover the filtrate with the filter paper. We pierce and make small holes on the filter paper cover and preserve the experiment for 7 days. We preserve the experiment for 7 days. So this is an experiment that now takes quite a long time. So we are saying that we are placing about 1 spatula full of copper 2 sulfate. Placing full of copper 2 sulfate. Crystals into 200 cubic centimeters of distilled water in a beaker. Now we are adding copper into distilled water. We stir while continue adding a little more of the hydrated copper 2 sulfate. Hydrated copper 2 sulfate. Crystals, and as we are adding now the hydrated copper 2 sulfate, we continue to do what? We continue to stir. Until no more can dissolve. Then we now filter and cover the filtrate with a filter paper. Now we pierce and make some small holes on the filter paper cover. Then we preserve the experiment for about 7 days. Now after having kept it for 7 days, we'll have observation to make. Now the observation begins as we are just right away as you are carrying the experiment. So large blue crystals formed when hydrated copper 2 sulfate crystals are placed in water. Large blue crystals are formed when copper 2 sulfate crystals are placed in water. They dissolve to form copper 2 sulfate solution. So now remember, the copper 2 sulfate itself, it's in crystals. Now those crystals, when placed in the water, they dissolve. So large blue crystals formed. Now remember, they are already crystals when we are placing them in water. So when placed in water, they dissolve to form copper 2 sulfate solution. After some days, water slowly evaporates, leaving large crystals of copper 2 sulfate. Now they are forming. The crystals are forming after having been placed in water, then left for some days. If the mixture is heated to dryness, small crystals are formed. When we are when the reason as to why we are not heating, what will form are just small crystals. What will form is just small crystals. Form They just form small crystals, so they dissolve to form so large blue crystals. When added in copper 2 sulfate, when so when hydrated copper 2 sulfate crystals are placed in water, they dissolve. They dissolve. They dissolve to form copper 2 sulfate solution. After some days, water slowly evaporates, leaving large crystals of copper 2 sulfate. If the mixture is heated to dryness, small crystals are formed. So the large crystals are formed because now we have left it for some days. We have left it for some days.